Good morning, and this video begins our very brief and quick tour of linear algebra and vector spaces. Um, there is material in here that coincides with mathematics. I believe it's 122. We're not going to spend all of the time on the topics that they do in there, but nonetheless, some elementary knowledge of linear algebra and vector spaces is very important for information retrieval. I hope you don't get too lost in this. I'm going to try to be brief. But the first thing we have to do is we have to talk about the whole notion of this thing called a vector. And what we need to do is we need to contrast that with just a simple point. So what I'm going to do over here is I'm going to assume that we have some coordinate axes here. So I'm going to draw an X and a Y plane here. So here is our Y-axis. Here is our X-axis over here. And the first thing that we can talk about is just some point P. And I'm just going to make some numbers up here. This might be -1, 3. And we know that what we do is we come over here and we go over -1 in the x direction, and then we go 1, 2, 3. And we draw a little dot over there, and we just say that that's P. Now, I want to come over here and I want to talk now about a vector A. And there are a couple of things that are going to be different here. Now, I'm just again going to make up some numbers here, but to distinguish a point from a vector, when we talk about vectors, we're going to draw an arrow over them. Just like that. And what is different here is as I come over here 1, 1, 2, 3, and now this isn't just a point. What this actually is it's a line with an arrow on it. And the arrow points like that. So there are two things that distinguish a vector from a point. First of all, a vector has magnitude. And a magnitude is it's a very fancy way of just saying it has a length. And the length of this vector, of course, is the distance from this point to that point right there. And we will discuss that in a second. The other thing that a vector has is a vector has direction. And there are lots of different ways of specifying a direction. One of the easiest ways to do it is we can just express it as an angle theta that it makes with the x-axis right over here. But the point is that the vector is not necessarily unique. We will note that if I come over here and I go over 1 and I go up 1, 2, 3, just like that. Believe it or not, these are exactly the same quantity, okay? They both have exactly the same magnitude, okay, and they also have the same direction. If I were to come over here and move this down to here, it would have the same angle that it makes with the x-axis. Likewise, if I came over here and drew this and went over 1 and then went 1, 2, 3, this is also exactly the same vector. Okay, so all three of these vectors are identical. So let's talk a little bit more about properties of vectors. Okay, so first of all, how do we find the length of a vector? So suppose I come over here and I look at this vector right over here. And what I'm going to do is I'm going to make another drawing of it. So here on the axes, and remember what I did is I came over 1 and I went up 3. So the length of this vector, well, the thing to note is if I come over here, you'll notice that I have a right triangle. Okay? And we know that the distance here is 1, and we know that the distance here is 3. And we know that this angle here, or this line right here, this vector, is actually a hypotenuse of this triangle. And we remember the Pythagorean theorem that says that a squared plus b squared is equal to c squared. So what happens over here is we know that 1 squared plus 3 squared is equal to c squared, or that c is equal to the positive square root of 1 squared plus 3 squared. So that's this over here. This quantity here is the length of that. So I want to just get into some notation here. If we have this vector A that is equal to 1, 3, if we want to talk about the length of the vector, the notation we use is as we draw these double lines, I put the name of the vector inside, and I do that, and I say that that is equal to, and in this case it would be 1 squared plus 3 squared, and I take the square root of it. Okay? Now, why don't we extend that? Nobody says we have to be dealing in 2 dimensions. We could be dealing in 3 dimensions or 5 dimensions or 20 dimensions. If I came over here, and you're going to have to pardon my artistic talents here, they're lacking quite a bit. So what's going on here is we have an x, we have a y, and we have a z. So we could imagine some vector, I'll call this vector b. And now this is going to be specified by 1, 2, 3. So that would say that we come over here 1, and then we go up 1, 2, and then we come out 3. And I'm not even going to begin to draw this for you. But if I wanted to come over here and say, okay, how long, or what is the magnitude of this vector? This, in fact, would be equal to 1 squared plus 2 squared plus 3 squared. And I would go ahead and take the square root of it. So if I wanted to generalize this, in fact, if I had some v is equal to some v1, v2, v3, all the way up to some vk, like that, then we would say that the magnitude of this right over here would be equal to, well, what am I going to do? I'm going to sum up all of the VI's. I'm going to square them. The summation is going to go from 1 up to k, and then I'm going to take the square root of it, like that. Okay? I hope that that was pretty simple. Why don't we keep it in 2 dimensions for now? It won't be taxing my artistic abilities too much. So what I want to do over here is, again, I want to come over here, and I am going to draw a coordinate axes. Like that. And I want to go back, and I want to assume that I've got some vector A. Why don't we say A is equal to, why don't we make it something like that? And why don't we have a vector B, which is equal to 1, 2. So first of all, if I have this vector A, so that's 1, 2, 3. And again, I will try to draw this as best I can. So that's the vector A. And the vector B is over here like this. And the question that I want to ask is I want to talk, how do I add vectors? Well, it turns out over here it's pretty simple. A plus b is just going to equal, I'm going to add the x components. It's going to be 3 plus 1. And then I'm going to add the y components, so it's going to be 1 plus 2. And that's equal to 4 comma 3. But geometrically, this actually is going to do something kind of cool. Now remember, we said that the representation of the vector is not unique. So in fact, here is the vector b, and what I'm going to do here, I'm going to change the color. This is also the vector b. If I come over to here and do that, and likewise if I come over here, this is also the vector b. And this is also the vector b. And now what I'm going to do is I'm going to take this vector here and I'm going to kick it upstairs one. So I could start over here and it goes over to there. This is also the vector b right there. Okay, so what I want you to notice here is here is the vector A, and then from here to here is the vector B. Notice I've gone from tail to head and then from tail to head. Now, if you look at this point right over here, that is 1, 2, 3, 4, 1, 2, 3. That is 4, 3. And what I have here then is that the vector A plus the vector B is actually equal to this vector right over here. And again, what I'm going to do is I'm just going to rewrite the picture down here. I went from here to here. That was the vector A. And then the vector B went over 1, 2. It went up to here. That was the vector B. And the sum of them was just that vector there. So if that's A and that's B, then this is A plus B. Pretty cool, isn't it? Now, I would like to, let me come back here, and I want to change colors again, and for some reason it is not letting me. That's okay. A minor glitch. I'm going to have pink axes. I want you to consider a vector A which is equal to 1, 2. So here's the vector A. And what I'd like you to do is I would like you to consider the vector 2A, which is equal to 2 times 1, 2 times 2, which is equal to 2, 4. Well, that's just going to be 1, 2, and then 1, 2, 3, 4. And that's just that way. And you can see that it has exactly the same direction as the original vector. What has changed is that the magnitude is different. Okay, so what we would like to do is just extend that idea, and we'll do it right here. Just let me get back my black pen. There it is. So let me come over here again, draw some axes. So the idea and what I'm going to describe to you has a name. It's called scalar multiplication. And the idea is basically this. If I have some vector v and I have some real number r, okay, I can multiply them together. Basically, if v is equal to v1 comma v2, and then I want to talk about rv, that would just be equal to rv1 comma rv2. And the idea here is that if this is my original vector, like that, that basically if r is greater than, well, if r is greater than 1, it's going to extend the line even farther. If r is between 0 and 1, it's going to make it even shorter. And then the interesting thing happens is what happens if r is negative? Well, again, let's come over here and let's pick this vector right over here. And so that is actually 2, 2. So let's suppose that v is equal to 2, 2. And I want to multiply this by minus 1. So I go minus 1v is equal to minus 2, minus 2. Well, that has the net effect, basically, is instead of the vector looking like this, we've basically just turned it around, and it looks like that. The vector minus 2 would start here and go over here. So it goes like that. And again, if I were to have minus 2v, okay, again, it's going to be twice as long. The magnitude will be twice as long as the original vector, but I've reversed the direction of where it's going. So this just brings up one final point that I would like to make in this particular video, and that looks like the following. Suppose here's my coordinate axes. And suppose I were to have the vector A is equal to 3, 1. And suppose I were to tell you that the vector B is equal to 2, 2. I want to know, what does A minus B look like? Well, first of all, A minus B, that is equal to the vector A plus a minus 1 times the vector B. Okay? And we know that minus 1 times the vector B is equal to minus 2, minus 2. So if I come over here and I look at the vector A, 3, 1, that's 1, 2, 3, 1. So that's the vector A. And B is minus 2, minus 2. So I come over to there. Okay, so that's minus B. And now, basically, I'm asking to add them all together. Well, remember, what I have to do is I have to go tail to head, tail to head. So what I've got to do is I've got to move this tail of B over to here. And then what I've got to do is I've got to go 1, 2, 1, 2. Like that. So we can see that these two vectors are exactly the same. And now we can see over here that this vector right over here, okay, this vector right here is A minus B. And we can see that A minus B, I'm going to have 3, 1, okay, plus a minus 2, minus 2. Well, I'm going to go, that's going to get me a 3 minus 2. And over here, it's going to get me 1 minus 2. And that's equal to 1 minus 1. And we can see over here that that's exactly where we are. We're at 1 minus 1. So that is vector subtraction, I guess I have one more thing I want to talk about. So I'm going to come over here and say save. And I think I have one more here. Yes, I do. Perfect timing. One more thing to talk about in this and then over. And this is very easy. Suppose I have a vector A and it's equal to 1, 3. Now, we know that we can look at the magnitude of A, and that's going to equal 1 squared plus 3 squared, and I take the square root of that, and we actually know that that's equal to the square root of, 9 plus 1 is 10. Now, I want you to come over here and I want you to think about if this vector here, vector A, has a length of radical 10, what does 1 over radical 10 times the vector A, what is the length of that vector? Well, first of all, this vector is equal to 1 over radical 10, and this is 3 over radical 10. And if I wanted to calculate the length of this vector, the length of this vector here, which we'll denote this way, I'll come over here and I'll draw the parallel lines, 1 over radical 10a. Well, that's just going to equal 1 over radical 10 squared plus 3 over radical 10 squared. And I'm going to take the square root of that. Well, that's just equal to 1 over 10 plus 9 over 10, the square root of that. And 9 tenths and 1 tenth is 10 tenths. That's just radical 1 is equal to 1. So what I've done here, this process right here, we've normalized the vector. And what normalization means is it means that we have created a vector that is of unit length. So basically, you can think about it this way. If we have some vector that's going out here, if we normalize it, we're just going to come over here and it's going to go in the same direction, but it's just going to have length 1. So basically, the vector A divided by the magnitude of A, this is the normalized vector. And we're going to have a special way of denoting that just because we're going to be doing this a lot in this class. And we're going to call it A, and we're going to put a hat over it like that. So one thing that we know right now is we know that the length of the normalized vector is 1. Okay, that is it for this video.